So in today's video, we are going to be talking much more and extensively about the concept of mutually exclusive events. We will also be talking about the usage of Venn diagram to diagrammatically represent two or more mutually exclusive events. We also talk about the mathematics that defines mutually exclusive events, and then we try to solve one or two questions to get us understand the concept of mutually exclusive events. So two events are said to be mutually exclusive if they cannot occur simultaneously. That is, these events can actually not occur at the same time. So let's take one or two examples. I'm going to assume the example of sleeping as an event and then you waking up as another event. So these two events are said to be mutually exclusive because you can never be asleep and be awake at the same time. So you are either asleep or you are either awake, but there is never a possibility that you are going to be awake and asleep at the same time. Another example of mutually exclusive events is, let's assume one of the events is you passing an exam and the other event is you failing the same exam. There is never a possibility that you are going to pass and fail the exam simultaneously. You either pass the exam or you fail the exam, but you can never fail and pass the exam at the same time. So that being said, let's talk about how we can use the Venn diagram to pictorially represent the concept of mutually exclusive events. And from the basic perspective, the Venn diagram is actually a diagrammatic representation that we use to represent the properties of sets. A Venn diagram consists of rectangles and circles, where the rectangle represents the universal set and the circles represents the given set. So let's take, for example, we have a situation of where we have three sets. So that simply means we are going to be having just one rectangle and three circles. And if we have a situation of us talking about just two sets, we have just a single rectangle and we have two circles. So let's try to translate this to the concept of mutually exclusive events. So the rectangle represents the sample space of the experiment and the circles represents the events of this experiment. So that simply implies that let's assume the experiment of the sample space of a football match. So the rectangle is going to represent the whole sample space, and for a football match we have just three outcomes, that is a win, loss and draw. So we have just three events in the sample space of an experiment. So that simply implies that if we want to represent the experiment of a football match using Venn diagram, then we are going to be having three circles and just a single rectangle. And since each of these events cannot occur at the same time, that is, it's never possible for a team to either win, lose or draw the match at the same time, so there's not going to be any form of interaction between those three sets. So the mathematics that defines mutually exclusive events or any event in the world of probability can either be the multiplication rule or the addition rule. And the addition rule for a mutually exclusive event is that probability into bracket A union B is equals to probability of A plus probability of B. We can also rewrite this as probability of A or B, which is also equals to probability of A plus probability of B. And since mutually exclusive events cannot occur simultaneously or they cannot occur at the same time, it simply implies that there is actually no intersection between the events. So that means probability of A intersection B is equals to 0, which you can also write as probability of A and B is equals to 0. And this is known as the multiplication rule of mutually exclusive events. So let's move into our worksheets to solve some questions about mutually exclusive events. So these are the three questions we are going to be using to explain the concept of mutually exclusive events. So let's start with the first question. The first question says that a card is chosen at random from a pack of 52 playing cards. What is the probability of a king or a queen? So in a standard deck, we have a total of 52 playing cards. So that means that we are going to say N is actually equals to 52. Now, how many kings do we have in a standard deck of 52 playing card? We have a number of 4 kings. So that means the number of king right here is actually equals to 4. And we also have 4 queens in a standard deck of 52 playing cards. So that means that the number of queen is actually equals to 4. So the question is, we should find the probability that you are going to have a king or a queen if one card is picked at random from the standard deck of 52 playing cards. So before we solve this question, let's try to use the Venn diagram to diagrammatically represent this question of ours. So the rectangle represents the universal set and then the circle represents the given set. So definitely we are going to be having 2 circles right here because we are talking about the king and the queen. So let's try to diagrammatically represent that. So we have our square right here. So we have one circle right here, and then we have another circle right here. As you can see, there is actually no form of interaction between these two circles, because once a card is picked at random, you can never pick both the king and the queen. You're going to pick either the king or the queen. So we have the universal set, which represents the sample space to be equal to 52. So we write 52 to be right here, and this represents the king and this represents the queen. So we have 4 kings right here, so this is 4, and we have 4 queen right here. So this is the diagrammatic representation or the Venn diagram for this question of ours. So the addition rule states that probability of A union B is actually equals to probability of A plus probability of B, or we can also write this as probability of A or B is equals to probability of A plus probability of B. So the event A in this case of ours is the probability of picking a king, and the event B is the probability of picking a queen. So that means in the context of this question, we have probability of king or queen, and that's going to be equals to probability of king plus probability of picking a queen. So the probability of picking a king, which is pk, is going to be equals to the number of king we have in the standard deck divided by the total number of cards. So that's the number of king we have is actually equals to 4 divided by 52. And when we do the math, we have our answer to be equals to 1 divided by 13. And the probability of picking a queen is going to be equals to the number of queen we have in our standard deck divided by the total number of cards we have. So that's going to be equals to 4 divided by 52 also, and that's going to be equals to 1 over 13. So now that we have the necessary probabilities, we can do the math. So let's take this towards the left. So probability of picking a king or a queen is going to be equals to 1 divided by 13 plus 1 divided by 13, and when we do the math, we have our answer to be equals to 2 divided by 13. Converting this value to decimal, we have our answer to be 0.1539, which is approximately 15.39%. So if a card is picked at random from a standard deck of 52 playing cards, we have a 15.39% chance of picking either a king or a queen. So let's go back to the second question. So the second question says that 2 fair die are thrown. What is the probability that a score on the first die is equals to 6, or the score on the second die is actually equals to 5? So this is question 1. We can just write this as question 1. So for question 2, we are talking about 2 die. So we have the first die. So let's say die 1. So the sample space of the first die is going to be equals to 1, 2, 3, 4, 5, and 6. And the sample space for the second die, which is die 2, is going to be equals to, we have 1, 2, 3, 4, 5, and 6. So the question is, what is the probability that you're going to have a 6 on the first die or a 5 on the second die? So probability of having a 6 on die 1, so let's just write die 1 right here, is the number of 6 we have on die 1 divided by the total number of sample space. So we have just 1 6 in die 1, and we have a total of 6 sample space in die 1. So that simply implies that we have 1 divided by 6. And for die 2, probability of having a 5 in die 2, so we have this as die 1. Let's just put 1 right here. Probability of having a 5 in die 2 is going to also be equals to 1 divided by 6. So the probability of having a 6 or a 5 is going to be equals to 1 divided by 6 plus 1 divided by 6, and that is going to give us 1 divided by 3. When converted to decimal, we have our answer to be equals to 0.3333, and this is approximately 33.33%. So let's move to the third question. So the third question says that a card is chosen at random from a pack of 52 playing cards. So what is the probability of a king or a heart? So there's a third question right here. So the standard playing card contains a total of 52 playing cards. So the number of kings in a standard deck is actually equals to 4, and the number of hearts in a standard deck is actually equals to 13. So the probability of picking